Alright, so in the last chapter we covered power, but now we're looking at power as it applies to energy in general, not just in electrical circuits. So power is defined as a rate at which energy is changed, and the equation for it, as you can see up there, is P power equals the change in energy over time. Now the change, if you remember, that just means whatever energy you started with, so your initial energy minus your final energy. And that is just the definition of that term, change in E. Now, another way we can look at that is through work. So, if you remember, work equals force times distance. So when we go to the next slide here, we'll have a couple equations, but we'll talk about that top one first. Work equals force times distance. Now, if you think about energy, if I'm trying to push a box across the floor, I have to put some energy in, and that box is going to move a distance, and that's how I know I put in energy. And obviously, since I'm pushing this box, I'm putting in a force. So I have my force, and it moves a distance, and that is how I measure my work. But that is also how I can measure the change in energy, because that's essentially what work is. It's the change in energy. Work is measured in joules, and it's how much energy is used up to push whatever object with whatever force a certain distance. So this makes us able to change our equation to this one right here. And that is power equals work over time. Notice I just replaced change in energy with work from this previous equation here. So I'm trying to simplify it and put it in terms of equations that you already know. And this is going to help you on your homework problems and in the supplemental problems. Alright, so we're here. We're at power equals work over time. Well, we know that work is equal to force times distance, so we're just going to replace work with force times distance, which is what happened in this equation right here. Work equals force times distance. There's force times distance. Add it in. And so it's basically the same equation. They all mean the same thing. You're calculating the same thing, but this is going to help you solve problems. For example, if I'm given force, distance, and time, and I was looking at this P equals change in E over T, I'm probably not going to be able to solve that problem. But if I look at it with this equation, P equals WT, I might be able to figure out work is force times distance. But it's even easier if I already know this. So I can take force times distance in any problem over time. If I have those three things, I can calculate power. But then what we are going to do is we're going to take this actually a step further. This is kind of a nice equation, but we have something else in here. And that is this lovely dt. So we have, if I were to take that out, it's distance over time, or meters per second. And that should look really familiar to you. You should be like, oh, hey, meters per second, that's a unit that I know. And that's because it's the unit for velocity, because velocity equals distance over time. So I can rewrite this equation yet another way, because if I'm given the velocity and I'm given the force, I should be able to solve this equation. So depending on what the problem gives me, it depends on what version on what factors I'm given that determines the equation that I'll use and how you use it. Keeping in mind, these are all the same thing. I'm just plugging in things that are equal to each other. I haven't put any numbers yet, but we will get to that in a bit. So if I plug in the velocity, or make dt velocity, it changes my equation to power equals force times velocity. So if I have a problem where I'm given a velocity and a force, I just have to plug it in and keep going. And you're going to find lots of different problems in your book that are going to use all of these different versions of it, but it's pretty much the same thing, and is summed up in that main equation, power equals change in energy over time. Keeping that in mind, we'll do an example problem. And that example problem reads, an electric motor lifts an elevator at a constant speed of 54 kilometers per hour. So that is the first thing. I know I have 54 kilometers per hour. What do I notice about these units? The first thing I should notice is this is not your typical meters per second, which is what you need. So you're going to have to keep in mind that that is going to have to be changed. But let's continue reading the problem. The engine must exert a force of 9 kilonewtons in order to balance the weight of the elevator and the friction in the elevator cable. So now we have another number. We have 9 kilonewtons. What power does the motor produce in kilowatts? So what we're looking for is power in kilowatts. So we figured out what we know and what we're looking for. So because we just did a bunch of different equations, I'm going to tell you, or we'll go through and pick which one that we need. So here we're given a velocity and a force. So if we go back just one, we find that P equals FV. F is force, V is velocity. I have both of my variables. I can calculate the power, which is super handy. So all I have to do is plug in my numbers, but first I have to convert them. So let's make this velocity into meters per second. So velocity, we have 54 kilometers. Let's make the line a little thinner there. Over 1 hour. Alright, so let's change kilometers into miles. So to get rid of kilometers, we have to put it on the bottom. And 1 kilometer equals 1,000 meters. I think I said miles. Did I? I hope not. And then we also want to get rid of hours and change that to seconds, which means hours is going to have to be on the top so that the units cancel out. And that's going to be 3,600 seconds. If I do that math, I should get 15 meters per second. So I have successfully changed my velocity into the right units. Now I have to do that with my kilonewtons, and kilo means 1,000. So this is really 9,000 newtons. So I have all of the right units now. I have velocity and a force, so I can go back and use this equation. And that's going to be, it's a little too light. P equals 9,000 newtons times 15 meters per second, which is going to give you 135,000. It's 135,000 watts. But if you remember from the problem, it wants it in kilowatts. So you get to kilowatts by dividing by 1,000. Just divide. You divide by 1,000 because kilo means 1,000. That's 3 zeros off. And your final answer is 135 kilowatts. So it wasn't too terribly difficult. There was a little bit of the hardest part of that was probably converting the units to meters and seconds and newtons, which are what you need to do the problem. And you need to keep that in mind with every problem you see. It has to be in those units, which might make them a little bit longer, but converting things to in the metric system is a huge part of science. If you have any questions, please leave them in the comments below. We'll be going over a couple of more problems. The next video is going to be on mechanical advantage. Please ask questions if you need to.